We discussed this. I want to backtrack a little bit. It's been a while. I was waiting. Somebody was going to do it. It's been a while. I was listening to that today, actually. CD in my top. Percent composition. We were talking about parts of a whole. How to come up with. If I ask you for the percent composition of a molecule in terms of the atoms that are in it, you should be able to calculate that. And what you will use to calculate that is some sort of conversion factor. When we dealt with equivalencies, like I used that slide I showed, like 8 legs to a spider, 4 legs to a chair kind of thing. If you know that you have NaCl, for example, is the formula that you're dealing with, you know that for every 1 mole of sodium chloride molecules present, you know that there should be 1 mole of sodium there, and there should be 1 mole of Cl. If you have CaCl2, calcium chloride, you should know that if you have 1 mole of Cl2, you actually have 1 mole of calcium and 2 moles of chlorine, right? Because you know that it's a 1-to-2 ratio. So you can use that to your advantage and use those as types of conversion factors to come up with what we call percent composition. We're dealing by mass, what we're doing, percent composition by mass. So you need to know the formula of the compound and the experimental mass analysis of the compound. The percentages, like I said, may not always be 100%. You're going to have they're going to be experimentally derived. So you're going to, everything's not going to measure out perfectly, but it should be close to 100. Let me ask you a question to prepare you for one of the upcoming labs. One of the things we also calculate is like percent yield, for example. How much of what you were supposed to get did you actually get? Now, if we do this, and let's say that you were supposed to, what you did was took a solution of sodium hydrogen carbonate, so baking soda solution, and you mixed with it hydrochloric acid. Imagine these two things coming together. If you have HCl and NaHCO3, what you will get is the Na from the sodium hydrogen carbonate can bond with, we talked about this in lab, right, the possibilities now that exist. One thing that sodium can come in contact with, remember, NaHCO3, HCl, guess what that sodium can bond with? Chloride to get salt, right? Now it stays dissolved, but if I wanted you to isolate salt, how do you think you could remove solid salt and isolate pure salt from that system? If you mix this all together, what do you think you could do? Because keep in mind, what you're going to have is NaHCO3, HCl, put them together, you could have H2CO3. If you remember from lab, I told you that things with acids with like carbonic acid with CO3 in it, it actually dissolves very readily into water and carbon dioxide, so all that's going to go away. You're going to be left with basically a solution of salt water whenever you mix those two things together because the carbon dioxide will escape. If you're left with the solution of salt water, how do you extract the salt from that salt water? Yeah, it's real easy. Evaporate away the water, right? Now, is it possible, use your head for a second, if you calculated that you were supposed to obtain, let's say 10 grams of sodium chloride, you calculated that was your theoretical prediction. I should, from what I know about this reaction, calculate 10 grams of sodium chloride. So that would mean if you actually obtained 9, your percent yield would be 90% of what you were supposed to. Is it possible to calculate a percent yield that would be higher than 100%? If so, how? Okay, maybe. Let's say that really the only thing that you had in there was salt and water, though. If I limit you to that, is it possible to still calculate a yield that's higher than 100%? How? If you say yes, defend it. How? First of all, how do you determine how much salt you would have? If you had it dry, if it was dried or whatever and you had it, you would put it on a balance, right? Put it on a scale. Notice I didn't say, is it possible to obtain a yield higher than 100%? I said, is it possible to calculate a yield higher than 100%? And it is. Because of what? Okay, maybe. More importantly, what do you have to do to get that solid salt? What if you have some water left in there? Even if it's a tiny bit, and there's some water locked up in those crystals that you've made, you got to realize that that's going to add to the weight. We said that we can't create stuff. You can't have 10 grams of sodium chloride and actually produce from this reaction 11 grams of sodium chloride. It's not possible. You don't have enough of these elements to do that. So what you're doing is you would be calculating a situation that didn't really occur. You would be wrong because you're just using math. Your process would be right, but you would have to realize that if you calculate 100%, or more than 100%, calculate that you've obtained more than you actually did, realize it's because you've got some water still and it's not 100% dry. It may look like it, but there's some water trapped up in those molecules. Even if it's just several molecules of water, that could change your results a little bit. So it is possible to calculate a situation that's over 100% yield. That doesn't mean that you actually got more than 100% though. Okay, anyways, that'll become more later when we get into that lab. Okay, so if we know this to be true, if we know that by mass, if we had a sample of sodium chloride, 39% of it was Na, then what we could do is assume a hypothetical example that if we had 100 grams, since we know that it's 39% sodium by mass, if we had 100 grams of salt, then 39 grams of it would be sodium. We can use that now as a conversion factor when we deal with grams, okay, like that. So we could go from grams of sodium chloride to grams of sodium by itself if we know this conversion factor. And the other way around. If we wanted to go from grams of sodium, how much sodium chloride could we make from that? We just use that same conversion factor. Flip it over. Right. Let's do a sample. It says percent composition from the formula. Remember we said this was ethanol. What is the percent composition of all the things that make up ethanol? Well, we're going to need to know the formula, which is given. Now, what we're going to have to do is figure up the total weight of this what's the molecular weight, the entire weight of this formula. And we do that because we said that on the periodic table, those decimal numbers that you see not only represent the weight in AMU, but it also represents how many grams 1 mole of each of those things would weigh. Okay? So just pretend that you had these represented moles instead of 1. Okay? Like if you had, for example, 1 mole instead of just 1 molecule of this, that means you would have 2 moles of carbon, right? C2. You would have 6 moles of hydrogen, 5 there and the 1 there. And you would have 1 mole of oxygen. Well, if you had that, how much would those weigh? Break it down. You see those came from the periodic table. Okay? So now you know that out of this entire, you would add this up, okay, and it would be 46.07 grams. Okay? That was the weight of the entire molecule. 1 mole of the entire molecule would weigh 46.07 grams. Now, all you got to do is take the parts, each one, and divide it by the whole, and you figure out the percent composition of that. So for carbon, take however much the carbon component of that molecule would weigh, divide it by the total, 46.07, you get 52.14%, and do the same for hydrogen, and do the same for oxygen. Now you've got percent composition, and you can start getting an idea as to how much of an element is present relative to the other element in these different types of formulas that we're dealing with. Okay, what is the percent composition of carbone if a 30-gram sample contains that much carbon, that much oxygen, and the rest hydrogen? If you remember this problem, one thing that we were missing here is the part of hydrogen, right? But we also know that we can get that because we know that the law of conservation of mass says we don't just create or destroy, we've got to account for it. So that means if I've got a 30-gram sample and I know that 24 grams of it's carbon, 3.2 grams of it's oxygen, then I have to automatically know then how much is going to be from hydrogen. Just subtract those two from that, and I've got the mass of hydrogen associated with that sample. Well, that makes it really easy because now I have the mass of all the parts and I've got the mass of the whole. So I can find percent composition very easily. So there's the parts. There's the parts divided by the wholes, and the whole, not wholes. There's your percent composition. Notice that it's mostly carbon. Okay. Now, there are actually, if you look at the chemical formula for carbone, you'll see that carbon is not the most abundant element in the formula. Okay. There's more hydrogens than there are carbon. However, carbon is a heavier element, so it constitutes more of what we would say the percentage mass of that molecule. Okay, now, I think this is where we're starting to leave off, empirical formulas. Now, what we can do with our knowledge, what we've gathered heretofore, is taking percent composition, knowing how to manipulate the periodic table, how to name things, how to use chemical formulas, that kind of stuff. And what we can start doing is taking data and figuring out what type of compound may be present in an unknown sample. You'll see that with all the labs, I try to always have some sort of unknown to that end. But one of the keys of finding out what something is to first deduce its empirical formula. In other words, you can't, there's no machine necessarily. I mean, it's not like it is on TV. There's no machine really that exists where I can just take this random sample, I just put it in one machine, I push a button, and it spits out every possible chemical that's in this sample that I have. It doesn't work like that, because what you got to realize in the way this all works is all these machines are able to do is to shoot different wavelengths of radiation, let them refract and reflect off of these different elements, and get an idea as to what elements are present in your sample. It cannot necessarily define each individual chemical, and it cannot necessarily tell the difference. Like if you know that there's a lot of carbon and a little bit of hydrogen and some oxygen in the sample, what those machines can do is give you a relative comparison. Like you've got about 50% carbon, 25% hydrogen, 25% oxygen. Okay, it'll give you sort of like percent compositions. Now what you would have to do is use your head, use some other instrumentation, take that a step farther, and you can start figuring out, if I know the ratio, if I know I've got twice as much carbon as I do hydrogen, what are my possibilities? What possible chemicals exist that would have that type of formula? Well, you got to realize too that when you get into a chemistry, C2H2 and C4H4 are two different chemicals. However, if you looked at data from them, you would see that both of them would have twice as many. Like if you looked at how much stuff was there, you would find that in let's do C2H2, you would see that you have as much hydrogen present as you do carbon in terms of atoms, right? If you look at C4H4, the same thing. You see that there's the same amount proportion. There's just as many hydrogen percentage-wise as there is carbon. So how do you figure out whether you have C2H2 or C4H4? They're completely different. They behave differently. It's going to be a huge difference in terms of maybe the toxicity of this type of compound, the volatility, how flammable it is. So you've got to be able to realize that when you have the empirical formula of something, what you have is the simplest ratio. So for example, CH is a 1-to-1 ratio. That's the simplest ratio. But you could have CH, C2H2, C3H3, C4H4, C5H5, and so on and so forth. You get the point. The empirical formula of that is just CH. That's the simplest ratio. So you've got to first determine what your empirical formula is. Then you can use that knowledge to move on and figure out what your actual compound is based upon what's different. You tell me. If I have something, let's say C2H2 and I have C4H4, what is the biggest difference that's easily measured, do you think, between those two things? Weight. Exactly. If we can take our empirical formula and then somehow figure out its molar mass, then we can figure out what our compound is. Okay? All right. We know that the molecular formula then will be a multiple of the empirical formula. Like C4H4 is a multiple of CH, right? It's 4 times CH, C4H4. That's what I'm saying here. Forget that. Okay. Sorry. Hydrogen peroxide is H2O2. You can see the three-dimensional diagram there. The molecular formula is H2O2. The empirical formula, however, is just HO. Look at benzene. Benzene is a ringed carbon compound. It's carbon bonded to itself, and it forms actual ring. And with each carbon, there's a hydrogen sticking off of it, C6H6. You can use it to dissolve stuff, organic things. The molecular formula is C6H6. However, the empirical formula is CH. All of the enes that you've heard about, if you ever hear anything with the suffix of ene, tend to have a 1-to-1 type of ratio in terms of the carbons and the hydrogen. So, okay, glucose, C6H12O6. Why is it a carbohydrate? Because its empirical formula is actually reduce all of those, divide everything by 6 in this case, you get CH2O, the carbo, and then hydrate because it looks like there's a water molecule present. There's not really, but it looks like it. Okay? They soon figured it out after they named them carbohydrates, that that's not what they actually are, but they kept the name because chemistry is not confusing enough the way it is. All right, so how do you find an empirical formula? Here's what you got to do. The first thing is, when you know your percent composition, You know how to calculate percent composition. You can do this now. You can just figure up the molar mass of your particular compound and look at how much each one weighs in that, and then calculate. You got a percentage. Okay, you've got a percent composition. Now, what you can do is, if you know the percent composition of your compound, is use that to calculate the empirical formula. But to do that, you have to convert everything to grams. Now, I'll show you what I mean. First of all, just realize that if you already have your data in grams, there's obviously no need to convert it. But what you'll want to do is, once you find your percentages and you assume like a hypothetical 100-gram sample, like if you know that, like I said a while ago, sodium chloride is 39% sodium by mass, that means if you have a 100-gram sample, you can use 39 grams, say 39 grams of sodium and 100 grams of sodium chloride. That's what I'm talking about with step 1. Convert your percentages to grams, hypothetical situation. Okay, now, once you have grams, here's what you got to realize. We now know that, first of all, what is a mole? Tell me what a mole is. More. 6.022 times 10 to the 23rd of anything. Okay? It could be atoms, it could be molecules, basketballs, elephants, doesn't matter. A mole is that many of them. Okay, now, does a mole of carbon and a mole of hydrogen weigh the same? No, of course not. So, in order to compare apples with apples here, what you have to do is, if you're going to say that I've got a percentage composition of like sodium chloride, and I know it's 39% sodium by mass, 61% chloride by mass, you got to realize that you can't just say that's it. You can't just say, like, the simplest ratio would be 39 to 61. You can't do that because they weigh differently. What you can use, though, is that mass to determine, because in chemical formulas, when you write chemical formulas, what do those little numbers mean? It means how many atoms are present, right? It doesn't mean how much they weigh. H2O doesn't mean H weighs 2 and O weighs 1. It means how many atoms are present. So if you're going to use grams, that's fine. But realize that you can use grams to count things, because you can use grams to go to moles. And if you know moles, you know how many things you have there. Okay? That's what we'll do. I'll show you with the work here. So you're going to need the molar mass of the elements. You'll get that off the periodic table. I'm just summarizing these steps, and I'll go through some problems with you. Then you write a pseudo formula. What's pseudo mean? Okay, so you're going to write some sort of formula that's kind of going to be like your formula, but it's not going to be the final form of it. I'll show you what I mean. Then you're going to divide everything by the smallest number to reduce. Sounds complicated, but you'll get the hang of it. And then I'll explain this. It's better if I just don't even try to tell you that now. I won't register. I'll just show you this when I give an example. Then you're going to have to clear your fractions, basically. You want whole numbers only by the time that we're done. That's what that last step explains. All right, so let's take a look at what I'm talking about. If you take some experimental data, how do you figure out what the empirical formula is for your compound? A laboratory analysis of aspirin determined the following mass percent composition. Find the empirical formula. You have a sample, okay? Based upon your sample present, you've ran it through some chemical instrumentation to determine the relative number of each type of atom present. You know it's a pure sample. Whatever it was, you just don't know what it is. Okay? So you've purified the sample. You just got to figure out what it is. Let's say it's 60% carbon, 4.48% hydrogen, 35.53% oxygen. What you now have to determine is, what is the formula? What is the chemical formula, empirical formula for aspirin? Okay? Here's what we know. Here's our percentages. Now, what we can then assume, just think about it. Okay? If I had a 100-gram sample, if these percentages are true, I would know this to be true. I would have 60 grams of carbon in a 100-gram sample, 4.48 grams of hydrogen, 35.53 grams of oxygen. Follow me? Easy enough. That means what I have created now are conversion factors using those grams. All right, how's that going to help me? First of all, realize this. I've got carbon, hydrogen, and oxygen present. If you look at that table that I gave you in terms of how to write things in what order, and always just realize when you have carbohydrate types of things and you have CHs and Os, that's always going to be the order. C, then H, then O. Okay? So you know that there's the skeleton form of your formula. What you've got to figure out are what numbers, how many of each are going to be present in the formula for this particular molecule. Okay. So this is what we know. You know that if you had 1 mole of carbon, you could look this up as you need it, but realize this is what you're going to need to know. You get this off the periodic table. If I had 1 mole of carbon, 12.01 grams, right? 1 mole of hydrogen would weigh 1.01 grams, 1 mole of oxygen, 16 grams. That comes off the periodic table. All right, so what we're going to do is take these new gram values that we have created in our hypothetical situation based upon our percent composition. We know this, okay? In a 100-gram sample, that is true. We take these gram values and convert them to moles. Because what moles will do is allow us to count atoms and fill in these here, these X, Y, and Z. Those have to be actual numbers, like how many of things are present. We use grams, realizing that we can use molar masses to get from grams to moles. Okay? And then once we get to moles, we can start figuring out what this thing is up here. What we can get then is what's called a mole ratio. I could get, I know how many moles of carbon are present relative to how many moles of hydrogen relative to how many moles of oxygen, and I can create a ratio up here where these numbers are. See what I mean? Then I can, from that, get the empirical formula. How do I go from grams to moles? I'm going to need the molar mass. Oh, I guess I didn't write those on there. I'm going to need the molar mass to get from here to here. Okay. If you look, how do I get from moles? How do I go from these gram values to mole values? If you look here, I told you we need the molar masses, right? If I have 60 grams of carbon, how many moles do I have? Convert it. You know that every 1 mole is going to weigh this much. So there you go. You have 4.996 moles of carbon if you had a 100-gram sample and it was 60% carbon. That's how many moles of carbon would be there. 4.48 grams of hydrogen would turn into 4.44 mole of hydrogen. 35.53 grams of oxygen would turn into 2.221 moles of oxygen. Now, what does this tell me? This tells me moles are actually numbers, right? A mole of carbon and a mole of hydrogen, although they weigh different, there's the same amount of each present. That's of utmost importance because now I'm comparing apples and apples here. I can say, for example, I could say this. I could actually write a chemical formula from this, and we're getting ready to. But I could say the chemical formula is C 4.996, H 4.44, O 2.221. Realize that I can say that because in a 100-gram sample, this is what it's telling me. That's the ratio of these things. I could write C that, H that, O that. Now, do you ever see anything written like that? No, that's ridiculous. Okay? So now, you've done the hard part. All that you have to do now is figure out how to express this in whole numbers. Okay? Like a normal-looking chemical formula. How would you do that? The first thing that you want to do is probably, remember, we're searching for the empirical formula, the simplest ratio of all of these elements to each other. What do you think the logical first step would be? That's right. Get rid of the smallest number. So I would then do what to all of these? Divide by 2.221. Now I've got 1 for oxygen, right? Now I'll have something different for the other two. Let's see what the next slide brings. It says divide all of these by 2.221, like you said. When I do that, here's what I get. Okay? I get C 2.25, H2O1. You'd obviously drop the 1, right? You don't write that, so you just write C 2.25, H2O. Does that look like an acceptable formula? No. Now, here's my problem. I've got to get rid of the decimals, right? But I'm at the point where I've already divided by my lowest thing, so, if I divide divide everything by 2, realize I'm back to a decimal over here. I've gained nothing. So I can't divide by any more, right? Because, if I divide by 1, I'll just get the same thing I have. If I divide by 2, I'm getting a decimal here, I'm getting a decimal here. I've actually backtracked instead of progressed. So what is the next logical step? What's something you can do to this but still maintain that same ratio? Okay, what number would I multiply by? 4, good. If I multiply everything by 4, I keep my whole numbers. and I maintain that same ratio, right? So if I multiply everything by 4, realize the reason I chose 4 was to get rid of this 0.25, right? What if I had like a 0.5 there? What would I have multiplied everything by? What about a 0.33? 3, okay? You could play with that. You'll get used to it. You'll see what I mean as you go through here. You'll have to pick a number that's close. When I do, there's my formula. I have deduced from that data the empirical formula for aspirin. It is C9H8O4. Now realize, I don't know at this point if it's actually that as my final answer in terms of what the formula is for aspirin, but I know that it can be reduced to that. Okay? So it could be C18H16O8. I don't know, but I do know that this is the empirical formula. I need one piece of evidence to decide for sure what the actual formula is, and it's the weight. I would have to figure out what one molecule of this actually weighed. If I knew that, I could figure it out, okay? And I'll show you how. But take a look here. Here's some different things. Well, these are sugars, of course. Glyceraldehyde is not probably considered an actual sugar, but if you have these, notice that these all maintain the same ratio of these elements. They all have the same empirical formula, but you could see that they are very different. Okay? They're different. And what you will see also is if you look at things with the same empirical formula, since each empirical formula increases by the same factor, you'll see that the weight, because it had the same proportion of elements present, the weight will increase by a certain factor as well every time. Look, 90 plus 30 is 120, plus 30 is 150, plus 30 is 180, because every time the empirical formula, the mass is going to increase by whatever the empirical formula weighs every time. So that would weigh, I don't know, what is it, 30, right? So since that's 30, you add another C. To go from here to here, you add another C, you add 2 H's, and you add an O, so you're adding 30 grams per mole every time you do that. So you should see a very steady increase in the molar mass as these molecules get larger if they all share the same empirical formula. That's useful. That will allow you to figure out what the actual formula of your compound is. So you know that the molecular formula has to be a multiple of your empirical formula. And we have to find out what the molar mass is. All right, let me show you. Determine the molecular formula. Keep in mind the difference. If you see these words, don't get lost in wording. Molecular formula and empirical formula, two different things, right? Molecular formula is the actual formula. Empirical is the reduced form of that. Determine the actual molecular formula of catenine if it has a molar mass of 204 grams and an empirical formula of C5H8. How do we do that? Now, we need to know the empirical formula, which is given. Now, understand that I've given it to you here. In real life, probably won't. I'll have you use the percent composition, calculate the empirical formula. Once you have the empirical formula, tell me the molecular formula if you know the actual molecular weight. Okay? I could ask one question on this test and cover a whole lot of ground. Okay? Not that I would do anything like that. You know that's not my style. But I could. All right. So, first of all, determine the molar mass of the empirical formula. Remember I told you a minute ago, if you look at that chart, if you know the molar mass of the empirical formula, you know how much to add each time as you go up from one factor to the next. So, okay, what is the empirical formula? If it's C5H8, how much does that weigh? What is the molar mass of that? Well, add it up. You've got 5 carbons, 8 hydrogens. Add them together, you get 68.11 grams. Okay? That is the molar mass for your empirical formula. Okay. What you want to do, it says divide the given molar mass, right, by the molar mass of the empirical formula, and then what you'll get is an answer that gives you how many times you had to multiply the molar mass of your empirical formula to get to that mass. That means that's how many times you multiply all the elements that you have present. Okay? I'll show you what I mean. If you know that the sample that I have is 204 grams, that's what you have, and you know that the empirical formula weighs 68.11 grams, how many times do you have, how many empirical formulas do you have? Do you have twice that? Do you have 3 times that? What do you have? That's what the point of this is. So if you know how much weight the total molecule is that you have, and you know how much every little unit of an empirical formula that you have present, you know how much that weighs, you can divide those and figure out that it's a factor of 3. So that means you would have 3 times whatever your empirical formula actually would be in terms of weight. So what do I do? How would I write that formula then if I know that it's got to be 3 times what you see there? What's the actual formula? Yes, C15H24 versus that. Okay? So there you go. Now, I want to go over this again since we got some time here, because some of you might have it, others don't have any idea what's going on or even what day it is. So I'm going to back up a little bit. I want to go over this again to make sure you understand it, because everyone always misses this. They think since it's the end of the chapter, realize there's a lot of information that goes into this. Okay, so you've got to know what you're doing here. I'm going to start with this one. Now, here's the percent composition. I'm telling you right now that a laboratory analysis of aspirin determined this as your mass percent composition. It could be, well, I mean, you're going to have to know. To answer that last question that I had, to determine the molecular formula, the actual formula, you're going to have to know the empirical formula to do that. Now, what if I don't give you the empirical formula? I could say calculate the empirical formula before you do all of that. To calculate the empirical formula, you got to know how to do this. You got to know that if you have a sample, you've got to be able to figure out what percent composition it is. If you have, NaCl and it weighs a certain amount, if you had 1 mole of it, how much would it weigh? If you know that there's 1 mole of sodium present in 1 mole of NaCl, figure out the part of sodium. How much does that weigh? Divide that by the total of what sodium chloride would weigh, and you get these numbers. Okay? You got to know how to do that. Now, once you get here, you can go from here to these percentages to the empirical formula, the most simplest ratio of all the elements present. Because all you've got to do is then realize what percent means. It means of 100. Okay? So 60 means out of 100 grams, 60 grams of it would be that. So you use that to your advantage and realize this allows you now to manipulate gram values that you may have in your experiment. It gives you conversion factors. I want you to write the empirical formula. You know it's going to be something like this. We just don't know what these X, Y, and Z are, for example. All right. Here's what we do know. This is the molar mass. Okay. So in order to, what we have to do, realize this. To come up with these ratios, to know how much of this versus how much of this versus how much of this, we have to use moles. Moles is the only thing, that's how we count things. Because what these numbers mean is how many carbons are there, not mass, not how much does a carbon weigh, how many of them are there. How many hydrogens are there? How many oxygens are there? The way that we do that in this class and with all chemistry is we don't count 3,217,719. That's dumb. We count it in moles. Okay, that's why we introduced the concept of moles, to group all this up together and to keep track of things. So we've got to get this gram values to moles. Can we go from grams to moles? Yes, we can convert from grams to moles because of what we've talked about on the periodic table. We know the molar masses of things. We know those numbers tell us how much 1 mole of it would weigh. We had 1 mole of it. Therefore, we have conversion factors. Okay, we can go from grams to moles. Now, if I can figure out how many moles of that, how many moles that is, guess what? I can put those numbers right down where the X, Y, and Z is. It tells me how many of them each are there. And then I can just start reducing and figure out what the ratio is. Okay? So I've taken mass, basically, turned it into actual numbers in terms of how much is there, and use that to come up with the formula. So grams to moles, use that to form a mole ratio, and then we can get the empirical formula from that. Okay, so there's my conversion. I take the grams of carbon, convert it to moles. Grams of hydrogen, convert it to moles. Grams of oxygen, convert it to moles. Now I can write C 4.996, H 4.44, and O 2.221. Then I just have to figure out how do I write that better than what it is. So like you say, it makes sense now to get rid of the lowest one. Make it something 1. So when I do that, there's what I'm left with. Now realize this is a nice example. When you do something like this in lab, good luck. with getting a nice 2.25, a 2, and a 1. Probably not going to happen. You're going to have some of these numbers like a 2.47, something that's going to be hard. You don't know what to do. If it's a 2.4, you treat that as a 2.33. Do you treat it as a 2.5? You multiply by 2, multiply by 3, multiply by 2.5. What do you do? Don't worry too much about that, because mostly that'll be experimental error kind of stuff. You get in the hang of how to run all this stuff. But realize in a nice lab with nice results, you might get numbers like this. Okay? Now, if you get numbers like this, how do you convert that into an actual meaningful chemical formula? Like you said here, it would make sense to multiply everything by 4 in that case to clear that decimal. If we do that, as long as we multiply everything by 4, we're fine. We maintain that same ratio as long as we treat everything the same. So C9H8O4. Okay? Now realize, to reiterate, here's your empirical formula. You'll see that as you go from C3, add a CH2O, you go to here, add another unit of that, you go to there. Every time, you increase in terms of mass by however much this weighs, right here. Okay? So, because of that, we can answer this type of question. Determine the molecular formula of cadmium if it has a molar mass of 204 and an empirical formula of C5H8. Now realize, I'm telling you that, I may not. You may have to figure that out yourself. In this case, it's given. So, what you're going to need to know is, in this case, it says that the molar mass of the empirical formula, to get the total molar mass, you're going to have to figure out, like back in this case right here, you look at this slide, what we're trying to figure out, come on, don't do this, is this. We go from 90 to 120, 120 to 150, 150 to 180. It's a factor, it's a value of 30 every time. What you're trying to figure out is that. We're trying to figure out that value. What is it, the actual mass of the empirical formula that we're dealing with here. So that's this. Okay? There's 5 C's, there's 8 H's, add them together, you get 68.11. So every time now, you increase. If you go from C10 to H16, it should be twice that. If you go to C15 to H24, it should be 3 times that right there in terms of its molar mass. Okay? So that means if I know its molar mass, I'm in good shape. Because if I know its molar mass, and I know how much the empirical formula weighs, if I divide that, I know how many times to multiply all the elements that I have in that formula. That's the point of this. So in this case, it's about 3. So I would multiply everything in the formula by 3, and I've got C15H24. That's my molecular formula. Questions?